So now that we've made a solenoid, or sorry, an electromagnet, we have shown that we can take a current carrying conductor that has some induced magnetism through it that goes in a direction, and they're called lines of magnetic force according to the direction of the current flow. We've taken that and then we have bent it, and we have shown that we can, now that's going to concentrate these lines of flux in the middle, and we called that a toroid. And then we bent a whole bunch of toroids on top of one another, which is essentially what we have in this situation. A whole bunch of toroids on top of one another are going to concentrate that magnetic field inside inside the space in between the coils, or inside all those toroids stacked on top of one another. And since it's so concentrated inside here, they end up, all these lines of flux end up working together. They went like this. I'm looking at the direction of these lines of flux must have gone like this, out of this side, all the way around and into this side. So I concentrated all of those toroids together. All the lines of flux from the toroid ended up, each of these circles was coming out from the inside, out of the left into the right, in this case, because of the direction of current flow. Then they all joined together and they made what we call an electromagnet. Now, there's a couple of ways to figure out that direction of flux in an electromagnet. I just did it by looking at each of these individual coils, and I know that each of these added up from the left to the right, so I know it came out of the left and into the right, and of course they're continuous all throughout, so we should draw those continuous all throughout. The other way to do it is to memorize the right-hand rule for an electromagnet. Right-hand rule for an electromagnet is different from the right-hand rule for a current carrying conductor. What the right-hand rule for the electromagnet says is, if you point your thumb to north, right-hand rule for electromagnet says thumb to north. How do we know that's north? Well, because the flux lines come out. Flux lines come out of North Pole. So if you put your thumb in the direction of the North Pole, then your fingers are going to wrap around your electromagnet. Your fingers wrap around electromagnet. Fingers. And reason you want to do that, you want to look at those fingers and they will show you something. They will show you the current flow. Now in this diagram, we already knew the current flow because we kind of started with that, because we can tell the current flow from down here. But this is showing you that if you put your right hand around an electromagnet, put your thumb in the direction of north, then your current must be flowing in that direction. So what you can also do is, if you know your current flow, this tells you the pole. So let's say I have this situation where a coil is wrapped around, and I know that north is here and south is here. Then I can put my thumb in the direction of north, and that will be telling me that, oh, the current must be coming around like this. It will tell me the direction of current flow. So that's the right-hand rule for an electromagnet. And why are electromagnets so important? Because now, instead of just having this bar magnet sitting on my desk, instead of just having this bar magnet sitting on my desk with a north pole and a south pole, I have this bar magnet, and I can turn on the current. I can turn off the current. I can switch directions. I can change the current to this direction, which will my make my north pole into a south pole and my south pole into a north pole. This is so useful in making relays, in making motors and transformers and everything. So our electromagnet is our step that took us from just a block of ferromagnetic material with a north and south pole always to one in which I can control and do useful work.